We're happy to invite Dor to talk about PCPs and hypercontractivity for global functions.
So thank you, Noam, and thank you all for coming to this talk. So in this talk, actually, there are not going to be any Fourier coefficients. There are going to be some Boolean functions, still the theme. But I'm going to tell you about how this notion of global hypercontractivity and all of this, much of what Max was talking about, was sort of motivated by some recent PCP stuff. So basically, I'm going to tell you a little bit about PCP without assuming that you're familiar with it too much. And then slowly but surely, we're going to convert to some Boolean analysis stuff. So here's the talk outline. So first of all, I'm going to tell you what is the PCP theorem. You know, the most basic vanilla PCP theorem from the 90s. And then some classical consequences of it. And this will show you the gap between what we know how to achieve from the PCP theorem and what we don't know how to achieve. And then we'll ask ourselves, how can we improve upon these things? And this will lead us to a strong formulation of the PCP theorem, which is better, but still not good enough. And this will motivate you against, which is really, you know, the main player here, which if we know that this is hard, then we know essentially everything. And we'll talk about the consequences. And then eventually I'm going to talk about this recent PCP stuff, namely the 2-to-1 or 2 games theorem, and how this is related to global hyperconductivity and all of this fun stuff. Okay, so let's start with the very basic. So here is a 3-sat formula. You know, we all know and love 3-sat formulas. And the most basic question you can ask is, I give you a 3-sat formula and ask you, is it satisfiable or not? So this seems computationally hard. We don't know how to prove it. So we just declare it that this is NP-hard, and we just assume that it's computationally feasible. And once you make this assumption that it is computationally feasible, then you can start proving that other things are also computationally feasible. And you know, this is the whole theory of NP-hardness. We even teach it in undergrad. So this is all very nice. This is the gold standard of as far as hardness is concerned. And how do you cope with hardness? Well, one way is to relax the satisfiability constraint and ask, I give you a satisfiable formula, please satisfy as many of the clauses as possible. So I don't ask you to satisfy everything, but I relax it. I tell you, please satisfy 99% or something like that. So this is when we talk about approximation or hardness approximation, this is the type of tasks that we have in mind. Well, with this in mind, one formulation of the PCP theorem says that even approximating 3-sat is still NP-hard, which is the following statement. It says that there exists an absolute constant C less than 1, so that even if I give you a 3-sat formula which is promised to be satisfiable, not only can you not find a satisfying assignment, but rather you are not even going to find an assignment that satisfies at least C fraction of the clauses. So this is much stronger than the standard Cook-Levin theorem. And indeed, you know, once we have the Cook-Levin theorem, we can start doing reductions, and the same thing goes here. Once you have the analog of the Cook-Levin theorem for approximation, you can start doing reductions and get hardness of approximation results for other problems. And of course, you know, because this is approximation, you cannot do all the reduction that you want. You have to do what is called gap reserving reductions, which is more complicated to do, but you know, we can still do it. And so once you're equipped with the PCP theorem and these reductions, then you can start proving a whole host of results. And indeed, here are a few results that are known using this machinery. So these are some very classical results. So for 3-sat, you can observe that if you just choose an assignment randomly, it's going to satisfy 7/8 of the clauses. And what Hassad proved is that this is essentially the best you can do. If I give you a satisfiable 3-sat formula, it's NP-hard to satisfy more than 7/8. For Maxcut, there is some factor which is 16/17. This is not tight as far as we know. And for each problem, there is some different factor that we know. Some of these are tight, for example, FLISAT, while others are not. For example, vertex cover or max cut. Yeah, set cover is tight. Well, depends if you want to fight about this little off one, but yeah. Okay, so let me just spell out some of these results just to get the general flavor of things. So one very basic problem in linear algebra is I give you a system of linear equations and ask you to solve it. And this is essentially the three-lane problem. So what is a three-lane instance? Well, in this context, because we're discrete people, we work over finite fields, and the most finite field is F2, so we're going to stick to F2. An instance of three-lane consists of a collection of equations, each one of this form. It has three variables, you sum them up, and you ask whether this is equal to B or not, or B is some constant in the field. So it's very easy that if I give you such a system of linear equations and I tell you that it's completely satisfiable, then you can solve it because of linear algebra. And it's also easy to show that whatever system I give you, you can always do 50% just by choosing a random assignment. And what Hastad showed is that once you relax the fully satisfiability, this 50% is essentially the best you can do. And he proved that it is NP-hard to distinguish between a system which is almost fully satisfiable and one where you cannot beat this half. This is one example of hardness approximation result that we know how to prove using PCP. Another one is about the clique problem. So yeah, so I assume that we all know what a clique is. So if I give you a graph with n vertices, it is NP-hard to tell whether this graph contains a clique of size n to the 1 minus epsilon, or it doesn't even contain a clique of size n to the epsilon. So if you take the ratio between these numbers, you see that it's hard to approximate the win factor, which is almost 1 over n. And this is, tight. But notice that in this case, even though there is a large gap between these two numbers, they're still small with respect to the number of vertices in the graph. It's not like constant fraction or anything like that. So here is the question. Can we get an analogous hardness result to the clique problem, but where at least in the yes case, we have some constant fraction of the vertices forming a clique? So as far as the hardness approximation ratio that you get, this doesn't change anything, but the problem clearly becomes easier. So it still makes sense to ask whether it is hard or not. But now, remarkably, this little change makes the problem much harder to understand, and this is partially understood. So let's say that I tell you that your graph contains a very, very large clique, like 50% of the vertices form a clique. What can you say then? So can you find a clique of size 50%? Well, this is maybe too optimistic. So maybe we can find a quarter, 1 over 16, or epsilon n. And we don't know how to do any of this. So we actually think that this is hard, but we don't know how to prove it. And it turns out that we need stronger assumptions to do that. So the PCP theorem, even with all of the extensions that we're going to see, seems insufficient to prove such statements. So what we're going to do next is try to discuss some strengthenings of the PCP theorem that were studied over the last 30 years with the aim of proving such statements. We'll see what they get and see how to get beyond them. Any questions so far? So to study these strengthenings, I'm going to make a different formulation of the PCP theorem, which is completely equivalent. It's just easier to see these strengthenings once we use this language of label cover. So here's the definition. So label cover is the name of a problem, a computational problem, and an instance of it proceeds as follows. So my instance, I'm going to call it psi, and it consists, first of all, of a bipartite graph. I have left side L and right side R. Then for each one of the sides, I have a separate alphabet. Sigma L is the alphabet of the left side, and sigma R is the alphabet of the right side. And one last thing, which is the most important feature of a label cover instance, is the constraints. For each edge in the graph, I have a constraint phi e, which tells me which pairs of labels to the left vertex and the right vertex are considered satisfying. And you see that there is this word projection here. So usually when you define label cover, you don't have this word, but we want projection, so I'm going to skip it. What is meant by projection is that these constraints are not arbitrary. Rather, they have at least mild structure. Namely, for each edge uv, once I tell you the label of the left side u, there is a unique label for the right side that satisfies the constraint. Or in other words, there is a mapping between the alphabet of the left side and the alphabet of the right side, so that if I assign the left guy the value sigma, then the right guy must get the value phi e of sigma in order for the edge to be satisfied. So this is what a label cover instance is. Of course, if I give you a label cover instance, so this is a maximization problem. And now I'm going to define what is the objective function of this problem. Well, I give you a label cover instance. Your goal is to assign labels to the vertices so that as many of the constraints are satisfied. So I want to maximize the number of edges E so that if I look at the labels that I assigned to the endpoints of E, then these fall inside the collection of tuples that are considered satisfying. So we'll see an example of how you can recast 3-sat in this language. This language is a bit abstract, but it captures many things and it's very useful. Let's see an example of how to capture 3-sat in this language of label cover. And for that, we should have in mind some 3-sat formula, G. And right now, I'm going to describe to you how to construct this bipartite graph, these alphabets, and these constraints, so that the label cover that we have essentially captures the satisfiability problem of G. So how does it go? Well, I need to tell you what is the left, what is the right, what are the alphabets, and the constraints. Well, the left, we're going to have a vertex for each one of the clauses. So these are these orange vertices. As for the right, we're going to have a vertex for each one of the variables. Now, what are the alphabets? Well, for each vertex on the right is going to get either 0 or 1, depending on if we want to assign that variable 0 or assign it 1. In other words, assignments to the left side describe assignments to the variables. And assignments to the left side, well, the assignment to each vertex here is going to specify the assignments to each one of the variables inside the clause. And I'm only going to allow 7 of 8 of the assignments, those that satisfy the clause. So this is how to think about the left and the right. And now the last thing that I need to do is describe the constraints. Naturally, well, if we have a variable here, x1, we are going to want the assignment that this x1 gets to be consistent with whatever it gets on the orange vertex. So this is going to be the constraints of the label cover instance. So we're going to have an edge between each clause and each variable if that variable is contained inside the clause or its negation. And we're going to demand consistency. So we're going to say that a label for this vertex is consistent with this if they give the same value to x1. And you can convince yourself that, in some high-level perspective, this label cover instance exactly captures the satisfiability of 3-sat, the formula G. It's not exact. The value is not exactly the same, but it really captures it in spirit. So whenever I say label cover, you should really think of this sort of instance in mind, but the definition is more general. So now that we have this label cover language out of the way, I can tell you an equivalent formulation of the PCP theorem. The theorem just says the following. There is some absolute value k and epsilon, so that if I give you a label cover instance where the alphabet sizes are constant, they're at most k, then it's NP hard to tell whether there are assignments to the label cover that satisfy all of the constraints, or all assignments satisfy at most 1 minus epsilon fraction of the constraints. So actually, if you do the construction that we did before, this is just a corollary of the previous formulation, but it's really equivalent. Changing last slides on the last minute is not a good idea, so I'm sorry about that. We're going to try to make it work. Let's see. Yeah, I hid the wrong slide. Anyway, we have the basic PCP theorem, and now we want to improve it. And well, as I said, this theorem as is strong enough to obtain some results, but it's not strong enough to obtain all of the results that you want. So you want to strengthen it, and there are 2 ways that you can think about in order to do that. So one way is to improve the soundness parameter. So in all of this business, I'm going to have 2 parameters, the completeness, which is what happens in the yes case. This is what you can do in the good case, and the soundness, which is the best you can do in the no case. So in the basic PCP theorem, well, you cannot do 1 minus epsilon, but 1 minus epsilon is still a lot, and we want to improve upon that. So this is what is called the low soundness regime. And you can hope to prove that maybe label cover is still hard, even if you want to distinguish between fully satisfiable instances and instances that are at most epsilon satisfiable. And this is indeed the case. We know how to do that. And this is proved using what is called parallel repetition theorems. So this was known for a long time, and really all of the results that we saw for fill-in, for click, and all of that, they already incorporate all of this machinery into the picture. Without this, we cannot really do anything. So this is one way you can try to improve upon the basic PCP theorem. Another way is more subtle, and in some sense, we already saw it. So the constraints in label cover are fairly generic. We don't have too much structure over them. Well, I'm slightly cheating already, because if you remember, I said this were the projection constraints, and clearly there are more general families of constraints. And this projection word is very important when you do reductions. But projection is still a very rich family of constraints. So you can hope to obtain stronger structure over the constraints. The more limited, the better. And this is not obvious. Like, you have to look at reduction and see that they actually use this structure a lot. But once you see enough of these things, it becomes clear that the structure of the constraint is very important. And here, unfortunately, our understanding is much more partial. And in some sense, so people have been doing this structure for a long time, but it looks like a hack. Like, every time you see this word smooth parallel repetition or smooth PCP, so this is basically a name for a hack to obtain some structure of the constraint, which is just good enough to obtain the result that the authors wanted. So here we have a complete understanding of this small value regime, but the structure thing is much harder. And as is life, if you want to obtain the best results, you actually have to obtain both of these things simultaneously. And I already said we cannot do it in the best way. And indeed, because we cannot do it in the best possible way, this machinery is still insufficient for many problems. So for example, we saw the word vertex cover. This is one prominent problem where these sort of tools are not enough. And if you want to obtain tight results, you have to go even further. But before we go further, the question is, so what would even be the ultimate combination between these two improvements? How would it look like, and what would it give us? So we're done with the basic PCP theorem. We're done with the consequences. And I did tell you what is the strong PCP theorem, which is basically the small soundness with some mild structure over the constraints. Now I'm going to tell you about this ultimate combination between all of these hacks, which has a name. It's called unique games. And this is a central problem in complexity theory. So what are unique games? Well, a unique game, first of all, is a special type of a label cover instance. And it has two additional features. First of all, the alphabet sizes of the two sides are the same. And in fact, you should think of the alphabet just being the same. And secondly, for each edge, this constraint between the alphabets is just a matching. It's the simplest possible thing, simplest type of constraint you can think of. Or equivalently, if you remember, we said that each constraint is defined by some map. So matching just said that that map is a one-to-one map. Again, label cover language is a bit abstract, so let's see an example. So let's say that we have our bipartite graph. Let's say that we have our vertices. And let's say that the alphabets is just some field, FP. Then what would be a unique game over this graph? Well, we have the edges. A unique game, for example, says the value that the left vertex gets minus the value that the right vertex gets is equal to 4 modulo P. In that case, whenever I tell you what is the value of x1, there is only one value for y1 that would satisfy the constraints, and vice versa. So this is one type of unique game. Actually, in some sense, it's the only type of unique game, but never mind that. And whenever I say unique game, this is really what you should have in mind. Okay, so we know what unique games are now. And the only thing that is clear so far is that unique games are just very, very special type of label cover instances. So in principle, they may be easier, computationally speaking. And for example, here is one aspect in which they are in fact easier. So if you remember, we said that if I give you a label cover instance, it's hard to tell whether it's fully satisfiable or at most 1% satisfiable. Well, for unique games, this is no longer the case. If I give you a unique game instance and I tell you that it's fully satisfiable, then you can just solve it, in polynomial time, because you guess the value for one vertex, and then you propagate it over the place. There is only one option each time you propagate it. So this is easy. Well, so what do you do then? Well, you conjecture that besides this little satisfiability issue, unique games are still hard. And this is what is referred to as the unique games conjecture, or UGC in short. This was made by Subhash Kot in 2002. And it says the following statement. It says, for every epsilon greater than 0, there exists some alphabet size k, such that if I give you a unique games instance file where the alphabets have size at most k, it's NPR to tell whether the instance is almost fully satisfiable, namely the value is at least 1 minus epsilon, or the instance is most epsilon satisfiable. In other words, the informal version of it is, if you ignore the satisfiability issue, unigames are just as hard as general label couple. And I have this silver thing because, well, I'll explain it soon. So NP hardness is, the gold standard. Silver is, silver is less than gold, so it's less. So this is a conjecture. It's still a conjecture, but there are many works saying, well, if this conjecture is true, then something else happens. So these are still very good results, but it's not NP hardness. So this is the distinction between gold and silver. And this is what I refer to as, the ultimate combination between small soundness and structure for the constraints. Because you see here the gap between the yes case and the no case is as good as you can hope for, but at the same time, I cannot imagine any, simpler type of constraints where this problem can still be conceivably hard. So this is really the best of both worlds. But of course, this is just a conjecture. So yeah. So this UGC business has been around the block for a while now. So naturally, there's been a lot of work on it. And roughly speaking, you can partition the work about unigames into 3 types. So one of them is algorithms. So naturally, once you define some computational problem, you can try to design algorithms for it. And indeed, starting with the original paper by Subhash, people have been trying to do it. And for some classes of graph, it works. For some classes of graphs, it works less well. But the bottom line is that all of these algorithms, while they're very sophisticated and nice, they're not able to solve unigames in general. So they don't break the conjecture. But they do give us fairly nice ideas about what we can hope that hard unigames would look like, or rather, what they cannot look like. This is one type of works that have been about unigames. The other type is the type of work that says, okay, let's assume that unigames is hard. What can we conclude about the world using it? So here there are many more works. I have only 3 citations here, but I don't want to flood you with gazillion. I'm not a cryptographer. So some very nice and neat results are tight hardness results for vertex cover. So you're probably familiar with the trivial 2 approximation algorithm for vertex cover. Where, you pick an edge, you pick the 2 vertices, and repeat. So it turns out this algorithm is essentially tight if you assume UGC. So this was a very nice work. But an even, I think, more influential work was this hardness result for Marxcut, which really opened the floodgates for consequences of unigames. And following this, there have been a lot of works. And I hope that I'm not offending anybody by saying that probably the most notable result in this business has been Raghavendra's result, that basically says that you can look at the class of constraint satisfaction problems, which is a huge class of problems, and assuming UGC for all of these problems, the best you can do is a semi-definite programming algorithm. So this is a really amazing result in my opinion. Like, it holds for a general class of problems. It tells you what is the best algorithm and why you cannot do better than it. So if UGC is true, then it gives us a very nice understanding for many, many problems. And the last type of works about UGC is, it's a conjecture. So let's try to prove it. And there have been some attempts, but as of today, the best, or I guess the most, the best result that we know about unigames is what is derived from the 2-to-1 games theorem, which is not equivalent, but it's basically equivalent to the following assertion, which says that the unigames conjecture is true, but in the yes case, you cannot achieve 1 minus epsilon, but rather some constant, say half. So this is the state of affairs about unigames. So let me elaborate a little bit about this consequence of unigames. So we're in analysis of PCS semester, so analysis should enter the picture at some point. And I will just say that behind almost every one of these consequences lies a very nice analytical theorem with Fourier coefficients, influences, everything that we like in this semester. So here is an example. This is this vertex cover result. And here is what it says. I give you an n-vertex graph. Then it's NP hard to tell whether there is a vertex cover that consists of at most half of the vertices, or every vertex cover must contain essentially all of the vertices. This seems ridiculous, but this is a consequence of unigames. In other words, when you do this division problem, you get that it's hard to approximate within factor 2 minus a little bit. Another notable consequence is this max-cut result that I said. So I hope that most of you are familiar with the Gomez-Williamson algorithm for max-cut. This is based on semi-definite programming. It's a very nice algorithm, and it achieves some funny approximation ratio for max-cut, which is roughly this number on the slide. And what you can show, again, assuming UDC, is that this algorithm is actually tight, in the sense that for every epsilon greater than 0, getting approximation which is just epsilon better than this is already NP-hard. And finally, I said that there is this very general result by Redovendra, and a slightly more slightly more precise formulation of it says that if I give you any constraint satisfaction problem, then you can write down the semi-definite program relaxation, which is something very generic. Then you can solve it, and then apply some black magic, which is called Gaussian random schemes that you have no control over, but it exists. And if you do all of these things without even looking at the instance too much, you get the best approximation possible. Again, assuming UGC.
Do you know what is this best approximation ratio?
Sorry?
Do you know what is this best approximation ratio?
Each constraint satisfaction problem has a separate number. I don't know if it's, I don't know if approximating these numbers is easy or some.
I think the same way it shows that there's an efficient program is actually confused.
Yeah, but there's some issue there on how loud of information you should look at. Yeah, I don't remember exactly this. I remember there is something that is not I don't know exactly, but there is some funny thing going on in the back.
They're achieved by finite size instances for any CSP with bounded area, right?
Yeah, but the question is, if the reality is k, how far you should go? I don't know.
It's quite bad.
Yeah,
I mean, it's still something finite.
Yeah, it's something finite, but and as I said, so we're in Boolean function semester. So behind each one of these results lies some very nice analytical theorem, and many techniques have been developed precisely to make these reductions work. And let me give you an example for one of these theorems, probably the most well-known one, which is called majority stay-based. So, still no fault. There are going to be Boolean functions, but no fault. So let's say that we have a balanced Boolean function, and let's take some correlation parameter rho. I encourage you to think of rho as close to 1, say 1 minus epsilon. I define the stability of f to be the probability that when I take x and y, which are rho correlated, so rho correlated in this talk is exactly as in norm stock and in max stock, the same thing. You keep the coordinates the same with probability rho, and otherwise you resample it. So you sample x and y, which are rho correlated, and you ask what is the probability that f assigns the same value to x and y. So this is the stability. And the question is, what function maximizes the stability among all balanced functions? Well, this is a bit of a boring question. It's just dictators. We've seen dictators today many times. And indeed, if you just take f of x to be equal to x1, you can calculate the stability and you can prove that this is the best you can do. So this is not an interesting question. And it turns out that for PCP, the interesting question is, what happens if you disallow dictators in a strong sense? What happens if I impose on you the constraint that f has no inferential variables? Then it turns out that the answer is much more interesting. And morally speaking, it says that among all of the functions with small influences, the one that maximizes the stability is the majority function. And the proof of this theorem, at least the original one by Moore, uses some very fancy analysis of Boolean functions, in particular hyper-contractivity, which we've seen, the invariance principle, which we haven't seen, but probably we'll see at some point in this semester. I should say that this theorem has multiple proofs by now. Some of these don't use any of these tools, and get even better parameters. But it's fair to say that the motivation for this statement came precisely because of the study of UGC, and this led to the development of some nice analytical tools. Yeah, you need negative, you need the bounded functions. Anyway, yeah, go on.
You didn't say, but the invariance principle was invented to solve this question.
Yeah, so the statement and all of the tools that were developed with were the main motivation, or the only motivation, was UGC stuff. And yeah, and since then, the invariance principle has found many other applications. So, okay, so next, I'm going to tell you a little bit about some progress about mini games, which is 2-to-1 games. So what is a 2-to-1 game? So as everything in this talk, a 2-to-1 game is a label curve instance, but you have some additional structure. So basically a 2-to-1 game is as close to unigames as you can get without being unique. In other words, now maybe the alphabets are not the same, but the left side is just twice as much as the right side. And now, if you look at the constraint as a graph, it's not a matching, but it's a 2-1 regular graph. So this is very natural. And here is an example. Again, we have our usual picture. We have a bipartite graph. And now let's imagine that the labels of the left side are elements from f2 to the k plus 1. And maybe the k plus 1 should be on the top. Doesn't matter. So this alphabet is twice as large as this alphabet. Think of it as vectors over f2 of length k plus 1 and k. Now, how would a 2-to-1 constraint look like with this regard? Well, here is one type of constraint you can look at. So suppose for each edge, I have some subspace. So again, this you should think of it as f2 to the k plus 1. So it's a vector space of dimension k plus 1. So imagine that for each edge, I have a subspace of codimension 1. Then what I can do is look at the label of the left side, project it onto that subspace, and ask whether this is equal to the vector on the right. So you can observe that because we are in f2 and we did a projection onto codimension 1, this is a 2-to-1 constraint because each projected vector has 2 lifts to the outer space. So 2-to-1 games have been also proposed by Court, and he conjectured that they are also hard. And if you notice, now we don't have this satisfiability issue, because when you do the propagation algorithm, it no longer works. So you can be optimistic about 2-to-1 games and hope that maybe they are hard, even in the yes case. We're asking to satisfy all of the constraints, and in the no case, we ask not to satisfy even epsilon fraction of the constraints. So formally speaking, this is what is called the 2-to-1 games conjecture. And the theorem, which, as I said, is equivalent to something, or roughly equivalent to something about unique games, says that, well, morally speaking, this conjecture is true, except for this satisfiability issue. In other words, for every epsilon greater than 0, there is some finite k, which bounds the alphabet size, so that if I give you a 2-to-1 games instance psi, it's NPR to tell whether it's almost fully satisfiable, namely you can satisfy 1/1 epsilon of the constraints, or it's barely satisfiable, namely you cannot even do epsilon. So let me quickly tell you what this theorem does give you. It doesn't give you all of the power. Roughly gives you half of the power of UGC. But here are some concrete examples. So as I said, it gives you hard gap for unique games between half and epsilon. Then you get some improvements for some classical combinatorial optimization problems. For example, you get a factor of square root of 2 for vertex cover. You get something for click, and you get something for max cut gain, coloring problems, and this and that. So I don't want to talk about too much about these applications. I just want to show you one of them, because this is the problem that we started with. So if you remember, I asked you, what happens if I promise to you that the graph contains a click of size half? Well, we cannot quite deal with that right now, but we can say that some different number, 0.29. So even if your graph contains a click of that size, you're not going to even be able to find a click of size epsilon. So this now we do know, but potentially this could go up to half. Yeah, so to infinity and beyond, as Buzz Lightyear said. So now we are going to go into more of the Boolean analysis type questions and kind of ask ourselves, so we got stuck about this unique games business. Then there is this 2-to-1 thing. And I'm going to try to argue that if you want to have any hope of approaching UGC or even this 2-to-1, you need to depart from these classical notions of hyper-contractivity and small cell expansion and go beyond that. So in the rest of the time that I have, I'm going to try to motivate why that is the case. And then in the next hour and maybe tomorrow, I'm going to say a little bit more about it. But I know it's going to be, some very light motivation. But before that, are there any questions before we switch gears? So turns out that if you want to prove PCP results, you have to use what is called error correcting codes. And more specifically, you have to talk about locally testable error correcting codes. So what is a locally testable error correcting code? Well, first of all, let's say that I have a code C, which is just a subset of sigma to the n. I'm going to say that it is locally testable if I have some tester T, a randomized tester. So the tester gets Oracle access to some word, probes a few locations, hopefully constantly many. And then based on what it reads, it decides whether to accept or reject. And I want two properties to hold. First of all, I want it to be the case that if my tester C is being ran on an actual code word for my code C, then it's always going to accept. Of course, you can relax it to almost always accept, but for us, we're going to deal with the perfect completeness case. So this is usually, it happens just because you design the tester in some sensible way. And the more interesting part is the soundness. And the soundness that I specified here is for what is called small soundness, and it proceeds as follows. Suppose I have some word W, such that if I run my tester on it, then it accepts with non-negligible probability delta. And how can it be? Well, one case is if I took an actual code word and maybe perturb it a little bit and did something to it, then it is most likely to be the case that the tester is still going to accept with good probability. My soundness property says that essentially this is the only way you can do it. In other words, if T accepts the word W with some non-negligible probability delta, then it must be the case that W is correlated with some actual code word C from the code. And this is sometimes referred to as the local to global phenomenon in the literature, but don't dwell on it too much. So here's an example, probably one of the more well-known examples. This is the Blum-Luby-Rubinfeld linearity tester, and it proceeds as follows. In this case, we have the code C, which consists of all of the truth tables of all linear functions from 0, 1 to the n to 0, 1. So this is an error correcting code. It's fully legitimate. And you can ask, how can we test whether a function is linear or not? So the most natural test, and this is the tester that they proposed, is as follows. Pick two inputs, x and y, uniformly at random, and query the function at 3 locations, x, y, and x plus y. And then just check that these values add up. Just check that f of x plus y is equal to f of x plus f of y. And if so, accept. So it's trivial to see that if f is linear, then the test passes with probability 1. And it's not hard, but not trivial, to show that if the test passes with slightly better probability than half, so half here is going to be trivial, just satisfied by a random function. So if you pass it with probability slightly more than half, then it must be the case that you are correlated with a linear function. So this is the type of test that we're after. And let me just mention one more parameter of interest, which is the number of queries that the tester makes. So in this test, the tester looks at 3 values of f. Namely, it needs to make 3 queries to the word. And the number of queries that the tester makes is going to be important for us. So for the rest of the talk, I'm going to focus on testers T that only make 2 queries. So I only allow you to look at 2 values of the function or whatever code we look at. So therefore, this type of tester is not going to be interesting for us. We're only going to want 2 queries. So here is a PCP conventional wisdom, which says that everybody believes that this is true until we don't. So the conventional wisdom is that if you want to prove a hardness result for some problem, let's say some constraint satisfaction problem, then in order to do that, you have to find a suitable code C along with a tester. And you need several properties to hold. First of all, the tester has to be complete and sound in the sense that we just defined. Secondly, the tester, so the tester, looks at some values, does some computation, and decides whether to accept or reject. So it turns out that, the conventional wisdom is that if you want to use this tester to prove hardness result for something, then the check that the tester does has to be of the type that you want to do. For example, if you want to prove hardness result for 3 lin, then the tester is going to have to look at 3 locations and check a linear equation in the 3 of them. So this is the first thing that you want. And the second thing is, well, error correcting cons, we think of them as encoding some message by a longer string. And the conventional wisdom says that you don't want the blow up of this encoding to be too much. And I should say that this reasoning seems kind of inherent. It seems that there is no way around it. But the other is a bit more technical in nature. Unfortunately, I'm not going to be able to fully tell you why it's necessary. This is related to a step in this proof that's called composition, where you take some PCP, you take your tester, and you combine them to get something nice. And when you look at it, you see that you don't want this blow up to be too much. And here's actually a good point to remark why UDC makes our life easier when we prove hardness approximation results. Because basically, if you are willing to assume UDC, then you can ignore this blow-up condition. Any blow-up would do. Therefore, if you want to design hardness results based on UDC, you just need to find a tester which is complete and sound and uses the right type of check, and you're good. And if you heard the word long code, then actually you don't have even much choice of what the code is. You just take long code. If anything exists, it will exist in long code. So it doesn't leave too much maneuvering space. So this is why UC is nice to have. But if you're not willing to assume that, then you need this blow-up condition. And I would like to argue that the two properties of the blow-up and the soundness are actually in tension with each other. So I'm soon going to tell you that if you want the test to be sound, then there is a graph that you can associate with the test that has to be a small set expander. Otherwise, there is no way this test is going to be sound. On the other end, if you have only a small blow-up in your code, it means that the code has less redundancies, like you're being cheap with the length, so there are less redundancies to play around with. Therefore, this limits the type of testers that you can choose. And naturally, when you don't have too much freedom in your testers, this means that you're going to have trouble making this test graph that I'm going to soon define a small set expander. So there is a delicate tension here between wanting the test graph to be a small set expander, but wanting it to be cheap with the blow-up. And this is where this conventional wisdom is going to eventually break. We're going to have to give up on one of these. But I'm getting ahead of myself. Okay. So in the last 5 minutes, I'm going to tell you what this test graph is and tell you why small set expansion seems inherent. So let's say that we have a code C where the coordinate space is n. Now I'm going to define the graph whose vertices are the coordinates of the code. And I have an edge between two locations if they can be queried by the tester T. So what is the tester essentially doing? Well, the tester is just picking an edge in this graph, querying the two locations and asking and deciding whether to accept or reject. And my claim is that if you want your tester T to be sound, then this graph GT has to be a small set expander. And the proof is going to be by a picture. So let's prove it. So suppose this graph GT is not small set expander. Therefore, it means that I can find some small set that has a lot of edges inside it. For most sensible tests, they have some symmetry groups. So therefore, once I have one set, I can find many sets. So let's say that I have a bunch of sets S1 to Sm that are disjoint. that together cover a large fraction of the vertices, and each one of them has individually expansion which is bounded away from 1. Then once I have this, then I can show you a word that passes the test with nice probability, but doesn't come from any code word actually. So what I can do is, I have these sets. For each one of them, I can choose a completely different code word and assign the coordinates in S1 according to C1, according to S2 according to C2, and so on and so forth. Then you can observe that because the tester, if it looks 2 locations inside S2, it's only going to look locally at C2, therefore it's going to accept. And because you cover a lot of vertices and inside each set a lot of the edges stay in, you can show that the tester passes with constant probability. But because each one of these sets is small, you don't actually have a code word globally. It's all a lot of small code words. Yeah, so this basically completes the proof of why small set expansion is necessary if you want your tester to be sound. So this is the moral. If you want the tester to be sound, you have to have an SSE. Or is it? So it is necessary. But what this suggests is that if we want to get over this hurdle, then we must give up on SSEs. We need to work with graphs that are not small set expanders and see how to get over this hump and try to do some other things. And in my next 2 talks, the one after this in 30 minutes and the one tomorrow, I'm going to tell you a little bit about how you can go beyond it. And I'm going to tell you about this Gaussian graph and all of the things associated with it, which sort of, which again were motivated purely by PCP perspective and where this lens of global hyper-contractivity really started. So I'm going to talk about this and we'll see where we go. So that's it for this talk. Thank you.
Are there any questions for Dor?
So this limitation, this SSE limitation, is something like that hold even for more queries than 2?
So it's more complicated to even formulate it for more queries. So for some problems, you're lucky. For example, for theorem, you're lucky because somehow you can allow yourself local correction using the trick theorem. So whenever this is the case, then this limitation doesn't really exist. But when you're not so lucky, then I'm guessing that some limitation of that exists. But I don't know how to define it. I never thought about it. I don't know how to define it for me.
And you can see with like the two-way where completeness over large enough. That's what you need, like a large enough alphabet.
But this depends on what is the problem you are trying to prove hardness for. So if you want to prove hardness for something with small soundness, you need to take a high alphabet. You can always do trivially soundness of what, like 1 over the alphabet size. If I want soundness delta, I need to look at that.
Let's thank Dor again.